So suppose we have a group of, well, really two groups of students. One of those groups of students is going to get extra math activities. The other group is not, but otherwise they're on the same curriculum. And we've got two different sample sizes. That's totally fine. The only time we need to have the same sample sizes is when we're doing paired data and there's some reason to pair, individuals up or responses up. So this is fine that we've got 47 students with activities, 38 without. So these activities are intended to, help math abilities. So there are kind of two, we'll look at two versions of a hypothesis test to see if they actually did help. So the first one is going to be determine whether the activities make a difference. So make a difference just means, right, some kind of change. It could be a positive change. Maybe the activities hurt, so it could be a negative change. I would imagine they wouldn't, but right, we're trying to see if it in some way made a difference. And then in part B, we're going to see kind of what we would suspect is that whether the activities enhance mathematical ability. So in both of these cases, the null is going to be the same, which is that really our means are the same. So mu1 equals mu2, 1 being the group with activities, so we could give that a 1, and then 2 being, right, population 2 being the students without activities. So our null is just that there's no difference. Our alternative would be, well, it depends on which case we're talking about. So in the first case, it would be that mu1 is not equal to mu2. And of course, this is not super fancy here. My mu1 doesn't have a subscript, and it's not actually the letter mu. In the second case, though, the case that we're looking at down here, we have slightly different alternative hypothesis. So the null is still the same, but now we're not just looking for some kind of difference. We're looking for a very specific difference, which is that the average for group 1, the group with activities, is larger than that for group 2. So it starts off the same, but it's not exactly so. Okay, most of this process is going to be identical. So let's go to stat, over to tests, and then think about what scenario we're in. So it's not a z-test or a t-test because those are for one sample from one population. We have two different samples, right? One sample for activities, one for without activities. So we're in a two-sample situation. And then we want to know, well, okay, is it a z-test or a t-test? Since we don't know sigma, it is not a z-test. We have the population, we do not have the population standard deviation sigma. We do have the sample standard deviation S. So we're going to be a two-sample t-test, right? We use the t distribution with our sample standard deviation S. So two-samp t-test. We go in there and we say, okay, well, we could have data if we had the raw data, but here we've got statistics. So some of these values are already put in. Now, the only thing I'll say to be careful about is make sure that the order you put them in is correct. In our table, n is the first thing listed, but in the two-samp t-test, x bar is the first thing listed. So just make sure that the order you have lines up correctly with the information in the table. So all of this should be in order with what we have. So we just kind of put in our correct values for the average, the standard deviation, and the sample size. And then, right, we want to know, this is all our alternative hypothesis. So mu1, well, in part A, we want this first thing, which is that it's not equal to mu2. We're going to say pooled. Well, we never pool these for our class. So we'll just say no unless otherwise told. So pooled, no, and then we're going to calculate. This will give us a number of different things. It'll give us our test statistic t. It'll give us a p-value. That's usually the most important thing we want. Degrees of freedom. Now, we have a slightly simplified version of degrees of freedom. So if you were to do all of this by hand, you might get a slightly different result. Because we would be using different degrees of freedom than this. There's a very complicated way of finding this. But for us, the biggest thing is that we have a p-value. Notice that we can scroll down. So if you down arrow, it'll give you some of these other pieces, standard deviation and n. We don't really need those. We already have them. So p is the most important thing that we want. So our p-value is 0.013, and I don't know, we'll go to one more decimal place. So 0.0133. Now this is greater than alpha, which is 0.01. So basically our sample results were not rare enough to reject the null. So we're going to say we fail to reject the null hypothesis. Right, what does that mean? We do not have statistically significant evidence to suggest that the math activities increased mathematical ability. Right, and basically we're saying, well, two things. First of all, I should say on average, because we're talking about averages here, right? It may have helped some students, it may have hurt other students, but if we look at them as a group, right, on average, then we don't have enough evidence to suggest that, sorry, not that they increased, that math activities altered or changed or made a difference in mathematical ability, since we're just looking for some kind of difference, right? Our two-sided alternative here. So that's sort of our only piece, right, is that we're looking for evidence to show that the alternative is true. We're hoping that we can reject the null, right, for something kind of, some sort of interesting result. But unfortunately, our p-value was a little bit too large, so we don't have enough evidence to say the null is not true. But this is sort of the type of conclusion you want to have in general is, you know, first of all, do you reject or fail to reject the null? And then, is that statistically significant? So failing to reject means we do not have evidence. We don't have statistically significant evidence. If we reject, then we do. All right, let's go to part B then and say, well, okay, great. We already talked about how our null and alternative look. The null is the same. The alternative is a little different. So if we go back into stat and then tests, we said we were dealing with a two-sample t-test. That hasn't changed. The only thing that changes, right, is our alternative. So mu1, we said we're testing to see whether that is greater than mu2. You know, did the activities actually yield better test scores on average? Again, we're not going to pool these, and then we say calculate. So here, let's figure out, you know, how all of this changes. So it's going to look something like what we had before, but we're going to get certainly a different p-value. So here our p is 0.0066. Now that is less than alpha. So that's actually important because that's going to mean that we have a slightly different conclusion than last time, right? Our alpha is basically a cutoff. So if our sample results occur less than 1% of the time, 0.01, under the assumption that the null is true, well then something suspicious is going on, right? We have really unlikely results. So we actually are going to reject the null hypothesis and say we do have statistically significant evidence of something. What is that something? Well, it's whatever the alternative is. So we do have statistically significant evidence to suggest that the math activities increased math ability on average. Right, and again, this is as measured by this aptitude test. So rejecting, right, we do reject is another way to say that. So we do have statistically significant evidence. Same thing, we do not reject, or we failed to reject. We do not have statistically significant evidence. So those two should kind of be in line. Again, this is all about the relationship between the p-value and alpha. And that's really the most important thing that we pull away from these tests. And it's, while there is a way to do this by hand, and we certainly could use our normal CDF or TCDF to help us out with these, this is the fastest way to go, is to use these tests. And then secondarily, the conclusion is just as important. What do we do with that information? So great, we have a p-value. What the heck does that all mean? And that's the bolded part that I've got here. What do we do with it in the context of this problem?